Welcome, my name is Luis Alberto Pérez. Long interested by scientific issues, I first read in 2006 in the internet an article from Professor Gabriel Barceló Rico Abello about the rings in Saturn planet and their possible interpretation via a very recent dynamic theory. It attracted me, and I followed up some works from the same author about the dynamic hypothesis he was proposing for particle systems forced to rotating simultaneous accelerations. I found two books from the same author on rotational dynamics and the theory he was proposing: Flight of the Boomerang, dated in 2005, and A World in Rotation in 2008. Later on, in the second volume, number 3, dated June 2012, of the World Journal of Mechanics, I found an article from Gabriel Barceló which was titled Analysis of Dynamic Fields in Non-Inertial Systems, in which there was explained the theory of dynamics interaction, and a video with experimental proofs that demonstrated the supported hypothesis from the theory. I read the referred article with a certain skepticism, as the mobile utilized in these experiments in the video did not seem to be really inertial to me, because it was propelled by an engine. Nevertheless, the issue was so interesting to me that I started the developing of a new experiments carried out on my own, designing for the purpose a clearly inertial mobile. After repeated tests using different mobiles, I was able to confirm the dynamic hypothesis the theory of dynamic interactions TDI exposes, even correcting the exception of the mobile inertial. In the present video, I am pleased to present the visible empirical result evidencing experiments carried out with a mechanical instrument that I personally have devised. The instrument is designed with the precise purpose to visualize on ground the behaviors of the TDI proposed by the Professor Gabriel Barceló Rico Abello. The physical tool I constructed for this test is, making use of the mechanic slang, a macroscopic body, a system of rigid solid particles mechanically able to give a non-accelerating inertial angular momentum to a solid uniform homogeneous mass revolving around its axis. It is also able to cause the mechanical action of a torque in the direction not collinear with said main angular speed. This torque is applied internally from within system, and still, as predicted the TDI, the deviation of the trajectory of the mass center of the instrument is visually manifested as shown then in the video. What this theory states is that, starting from a rigid body or a system of material particles that has a linear movement and also an intrinsic angular momentum, this is a non-zero angular velocity, when the system experiences any angular momentum per share a moment of force, torque, not collinear with the principal intrinsic angular momentum, then something specific takes place. The center of mass of the system shows a variation of the initial straight line in direction, a deviation from its initial straight path. The velocity fields generated by the so-called resulting torque or dynamic interaction torque are dynamic consequence of the joint action between the main angular momentum and the secondarily applied non-collinear torque. The momenta, inertial inhomogeneous fields, velocity fields or momenta of rotation particles, generated as a result of a secondary torque, what is called angular precession, are added to the closed system rectilinear momentum vector. This is, they dynamically engage to the entire inertial motion of the system. In short, the phenomenon is due to the fact that these fields are dynamically coupled with velocity fields that pertain to the rectilinear displacement of the system's center of mass. This form of path deviation is predicted and described by the TDI by a simple equation, so that the resulting vector is related to the initial one via a rotational operator. The radius of curvature given at any given point of the system mass center trajectory is extracted through the mentioned equation. The evidenced path answer to algebraic additions, couplings of inertial fields or velocity fields.
Despite the difficulties in performing the experiment on Earth instead of in space, with the unavoidable negative accelerations due to friction with land surface, air and also the existing one in the bearings and motors, it has been possible to perform the test and watch it in this video. If there were no such frictions, the measures that could be taken of the speeds as well as of the instant radii of curvature hypothetically would verify the theoretical framework that Professor Barceló exposed in his theory of dynamic interactions in his publications and articles. This is the instrument used for the tests. It is equipped with a central metal disc which is initially provided with a principal angular momentum. It is also provided with a clamping bar or sheet, shown in wood color, on each side of the disc in which center the motor stator core that moves the disc is fixed. At each end of the mentioned sheets, the stator of a servo motor is fixed, which will perform a non-collinear secondary torque to the disc. The rotor of each of these servo motors is fixed to a ring which holds the entire structure. While the disc is still, if we activate the servo motors, this is what happens to one side and to another. As said, in the center there is an engine that gives the main angular momentum to the disc. Once the disc has an angular momentum, if we activate the servo motors, then we apply a torque in a right angle to the main angular momentum, and this is what happens. In one direction and in the other. It is shown in blue the velocities field generated by the torque of dynamic interaction. The direction of these fields is reversed depending on which way we activate the servo engines. The new dynamic hypotheses, as proposed by Professor Gabriel Barceló, are empirically demonstrated when these fields, shown here in blue arrows, are dynamically coupled with any inertial field of a possible rectilinear inertial momentum of the system. In order to perform the test, the instrument operates standing on wheels on a flat, smooth surface. An impulse is given, so it acquires a rectilinear inertial momentum, for example in line with the indicated arrow. The generated velocity fields, shown in blue, are dynamically coupled to the rectilinear inertial field, giving as a result a deviation of its trajectory in the indicated direction. If the system is manually driven to another inertial rectilinear momentum, the generated fields caused by the interaction torque, shown in blue, are also added to this rectilinear inertial field. As a result, we get an increment of the said last field with respect to its direction, this being in the indicated direction. In the sequence we have just seen, the system operates upon a flat and smooth surface by means of non-gyratory wheels. This sequence is performed with the system supported on gyratory wheels. The system has initially an inertial non-accelerated angular momentum as well as a rectilinear momentum, also inertial. It is important to note that the secondary torque is activated perpendicular to the principal angular momentum after the main engine is completely inactive. The system initially must have intrinsic angular momentum, which we will call main angular momentum. When this is happening and a torque is operated on the solid normal to the said main angular momentum, the generated velocity fields are shown in blue, being the yellow arrows the fields that would be generated if the solid lacked a main angular momentum. The inertial field, shown in blue vectors, is coupled. It is vectorially added to any velocity field available to the system's center of mass. In these scenes, note that this instrument rests on a slightly inclined surface in order to provide the system with inertial movement. Being both moments, rotation and translation, of an inertial character, the secondary torque is activated, and it is evidenced that the system's center of mass deviates the direction of its rectilinear velocity vector. The substantial difference between this experiment resting on gyratory wheels with the submarine test developed by Gabriel Barceló is that in this case, the rectilinear momentum and the main angular momentum are both inertial, although negatively accelerated due to multiple frictions. We now describe the conceptual elements of the experiment, pointing their position in the test instrument. Vector straight momentum, main angular momentum, secondary torque, direction of inertia generated fields, the velocity fields in the complete system are dynamically coupled with the generated velocity fields, leading to a variation in the direction of the system's center of mass.
From the study of this and other phenomena derived from observations of bodies endowed with angular momentum simultaneously suffering the action of some torque not collinear with them, we conclude the need to persevere further in these studies. The fact about having ignored these assumptions, which are an important area of non-inertial dynamics, may have been due to the lack of suitable mathematical tools. We therefore suggest finding a new mathematical system, a new algebra that doesn't exist yet nowadays, to understand the rotational dynamics, and also the need for a new drive in the further research and study of velocity fields or inertial fields in baryonic matter.